Hey, good morning and welcome back. My name is Candlepool and I will be taking you through the MHC class 2 binding prediction tool. So in the previous session, Edita did a great job in explaining the class 1 prediction tool. So here's a brief outline of what we'll talk about in this session. First, we will have a brief comparison of class 1 and class 2 tools, and then we will go through the overview of the class 2 prediction tool. We'll see an example and all the descriptions. And I will also, on the way, I will also be giving the guidelines on how to use the tool, what the different versions. We have 3 different versions where in the standalone and the API or RESTful interface. And I will also be explaining the prediction of promiscuous binders, and we have on a new approach, new strategy to predict top immunodominant vectors. I will be explaining that one also. And I will also explain the other resources available. And at the end, we have a short exercise that you can try. So let me start with a comparison of the class 1 and class 2 tools. So the basic structure and principles are same as the class 1 tools, which Edita already explained in detail. So I'm not going to explain whatever is same with the class 1 tools, but you will still find some of the slides redundant and duplicate. Please bear with me. And if you have any questions, please stop me and you can ask me. And there are some differences between the class 1 and class 2, which I will explain in detail, and you can also ask me if you find anything confusing. Okay, so the major differences between the class 1 and class 2 tools start from the structure of the class 1 and class 2 molecules, MHC molecules. So Edita showed the basic structure, 3D structure of the class 1 molecule, and here you can see, this is the class 1 MHC molecule and this is the class 2 MHC molecule. So here in class 1 you have only one chain that actually, the alpha chain that impacts the binding. Whereas in case of class 2 you have both alpha and beta chains that impact the binding, peptide binding. And another important difference is that in case of class 1 the peptide binding groove is closed. So it can accommodate only shorter peptides. So for example from 8 to 14 in length. Whereas in case of class 2, the binding groove is open and it can accommodate longer peptides. So these structural differences and the differences between class 1 and class 2 molecules actually poses a challenge for designing the class 2 tool. So the designing the class 2 tool is not as easy as class 1 prediction tool. And here I just want to touch on the nomenclature for the class 1 and class 2. So normally we see that for class 1 we mention only one chain. That the reason is that I mentioned earlier that only one alpha chain is variable in case of class 1. In case of class 2, both alpha and beta chains are variable for DP and DP loci. So where we mentioned both the A chain and B chain in the allele nomenclature. In case of DR locus, only alpha chain is variable. So we just mentioned only the the beta chain. So coming back to the challenges in case of designing a class 2 prediction tool. So I mentioned that it can accommodate longer peptides, anywhere from 30 to 25 amino acid length. But not all these residues bind with the MHC molecule. So there is a binding core composed of 9 amino acids which actually binds with the MHC molecule, the binding groove. So we have to, when we develop the binding prediction tool, first we need to identify the binding core within the longer peptide. So it need not be in the exact middle of the peptide, it can be anywhere within the peptide. So we need to identify the binding core. So it's a challenge for during the design of this binding prediction tool. So we need to have proper alignment of the binding core with the binding groove. Another thing is, so we have the binding core here and we have some flanking residues on both ends. So these flanking residues also impact the binding. So these residues will be interacting with the MHC molecule on both ends. So the composition and the length of these peptide flanking residues is also a factor that needs to be considered when we develop the prediction tool. And other challenges is that we have less data for class 2 binding compared to class 1. So we have so many alleles available for prediction. You can see the class 1 binding prediction tool, we have got so many alleles for which we have got algorithm available. But in case of class 2, we don't have that many alleles available, and the species is also limited. We have only human and mouse. For mouse, we have only few alleles available for prediction. That's one of the reasons is that we don't have much binding uniformly measured binding data available for developing the algorithms. So these are some of the challenges that we face in case of designing class 2 prediction tool. And because of these reasons, the prediction efficacy is a little lesser compared to class 1 prediction tool. So class 1 prediction tool gives a very good performance, but the performance for class 2 is not as high as class 1. And another difference is that for class 2, the length is fixed at 50. So whatever length of sequence you input, it will give only 15 words. So in class 1, you have the option to choose whatever length you want, like from 8 to 14, but the length is fixed at 15 for class 2. That's for the tool purpose. It's not that the MHC molecule always binds with 15. It's not like that. But for the tools, for different reasons, we have set the length at 15. I will explain why we chose the length of 15 in a later slide, but that's the difference between class 1 and class 2. And mainly because the prediction efficacy is lesser compared to class 1, we have to set a higher threshold for selecting binders in case of class 2 compared to class 1. Okay, so those are the major differences between the class 1 and class 2 tools. And now we will go to the web class 2 binding prediction tool. First, we will start with the web online version. So the basic structure, as I mentioned earlier, is exactly the same as the class 1 tool. On the top, you will find all these tabs for different resources. And here is the text box for inputting the sequence. So you also have other options for inputting the sequence. For example, you can upload your sequence file here, by clicking here. And then you can select the sequence format here. And the next major thing you need to do is select the prediction method, same as the class 1 tool. And then here you have to select the species and locus, and then next select the allele. So the basic structure is same as the class 1 tool. And here you will see a link for browsing the sequences from MHC. So if you click on that link, you will see a sequence browser. So don't confuse, this will not input the sequence by itself. It cannot import the sequence automatically. You can just find the sequences of your interest by going to this taxonomy browser, and you'll have to copy and paste the sequences into the text box. So the next one is method. So once we input the sequence, the next step is to select the method. So we have different methods available here. So here's where you select the method. Similar to class 1 tool, we have got different methods available, netMHC pan and netMHC toolpan. So in case of class 1, we call it netMHC pan, and here we call it netMHC toolpan. And we have NN align, both are based on artificial neural network. And we have got SMM align based on stabilization matrix alignment, and then we have got combinatorial library and Antonio law. And besides this, similar to class 1, we have consensus method, which employs a combination of SMM align, NN align, and combinatorial library or Antonio law. So the users employ 3 methods. And further, we have got this IEDB recommended. So if we have got algorithm for the allele that we chose among these ones, we will use consensus. If we don't have, then we will use the netMHC toolpan. So it's same as the class 1, which editor already explained. So now we have got all these different methods. Now the first question is which method to choose. So normally what we recommend is to use the IEDB recommended, same as the class 1. So the benefit is that it uses the best method. It's a combination of NN align, SMM align, and combinatorial library or Antonio law. Or if we don't have an algorithm, we use netMHC toolpan. So this gives a better performance than individual methods. So we have our team, our lab has done a study, and it was found that this consensus method gives a better performance than individual methods alone. And another advantage is that when you use the consensus method or IEDB recommended method, it gives a consensus percentile rank for binding affinity and percentile rank for each method separately, and also a consensus percentile rank. So editor already explained that. I will also explain it in coming slides. So these are the advantages, major advantages of using this IEDB recommended method. So the next step is to select the allele. So this is slightly different from the class 1. So here you can see the there's a drop-down menu where you can choose the species and the first. So here you put human and mouse option for human and mouse, and within the human you will find the local DP, DQ, and DR. And for DP and so you can select. So first, by default in the drop-down menu, you will find some of the alleles which are the most frequent in the global population. So if you select the DP allele, I'm having trouble with this. Okay. So by default, when you click the DP allele, you will find 5 alleles which are the most frequent in the global world population. And if you want to select, so this is a combination of alpha and beta chains, which are the most, most frequently occurring combinations, most frequent in the world. So if you want to select alpha and beta chains separately, there's an option for that. You can check this box here, select alpha and beta chains separately. And if you check this one, you will get 2 drop-down menus where you can select alpha and beta chains separately. And the next option is there's another link or another checkbox here for selecting HLA allele reference set. So if you check this one, there's a set of 27 alleles, most frequent alleles in the world, like the alleles with the highest allele frequency in the world is chosen as a reference set. So if you want to do predictions based on those reference sets, you can click this one and all those 27 alleles will be selected. So in case of last one, you will have to select the length also, but here you don't have to select the length because it fixed at 50. And more information on this reference set and the frequencies is given on the help page on section 3. So if you go to the help tab on the top, more information is given here. And there's one more option to upload the alleles. So if you happen to do more repeated analysis with the same set of alleles, you don't have to drop down, select the alleles from the drop down menu. You can make a text file and you can upload that allele file. But you have to remember that it has to be in certain format. The allele has to be in certain format. And more information is also available on the help page. So those are the major points to remember when you are inputting the data, your input parameters, how to input the sequences, how to select the method, and what we recommend using the IEDB recommended method and why it's better than individual methods, and what are the different options for selecting alleles. So next, let's see what happens. Yes.
Can you do the combination of all?
No, you can do that. Yeah, first you select human locus and then select whatever allele you want, and then next you can change that to mouse and then select that. Yes. You mean the uploading?
Yeah.
So first question was whether we can give both human and allele the same file to upload. Yes, you can do that. So whatever alleles you want, here in the example, even the example shows that, you can do that. Whatever alleles you want, you can just list in that text file and you can upload that, possible. So now you have got all the input parameters, and let's see what happens once you submit the sequence. So what the tool does is, first of all, it breaks your sequence, your entire protein sequence into all possible 15 So these 15 will be like, for example, will be overlapping by 14, starting from one segment to, amino acid will be 1, 2, 3, so on. It will generate all possible 15 and then it predicts the binding affinity for each peptide, and based on the method that you chose. And further, it compares the predicted affinity to that of a large universal set of peptides that we already have. So we have a set of peptides collected from the Uniprot, like around 200,000 peptides, and it has a set of predicted binding affinity. So we predict the binding affinity for each of the peptides in your protein sequence and compares it with that one, and it assigns a percentile rank. That's how we generate this percentile rank. So it's generated by comparing the predicted binding affinity of your peptide with that of a large set of peptides. And in case of consensus, as Editech,
that's the same for every.
Yes.
So how big is 200?
Yeah, around 200,000. 200,000, yeah. And then And then the consensus picks the median rank of the methods used. So for example, there are 3 methods used. In case of consensus method, it employs 3 methods, and the consensus means it's the median of the 3 values. So it's further explanation for the consensus personnel rank. So how it's generated is the personnel rank. So this is kind of important for us because that's the scale how we determine the binding, binding efficacy of the peptides with allele. So it's generated by comparing the selected peptides predicted binding affinity against that of large set of peptides. And why we use that? Mainly because it gives a uniform scale for comparing across different methods and between different peptides. So different methods, for example, you take neologism, SMM and NLL, it will have its own scale of prediction. So, but if you have a same uniform scale like this, a personnel rank, you can compare between different methods and different peptides. And a lower personnel rank indicates higher affinity. And in case of consensus, it's the median of the 3 methods that's used. So now let's see an example. You don't have to do this. It's not an exercise. It's an example. I just want to show how you will be doing it. So here the question is, it's a simple question. Predict the peptides in the NS3 region of hepatitis C virus polyprotein that binds to the MHC allele DPB-0401. So I have only given the B chain here for the DP locus allele. So first, I take the NS3 region of hepatitis C virus. I copy and paste it into the text box. And then I select the method as IEDB recommended. Then I choose human, BP locus, and then select the allele. So we have in the default drop-down menu, we have got this combination of DPA-01 and DPB-0401. So I just select that one. I don't care much about the alpha chain, and I select this one, the B chain. So this is how you get the results. So this is also same as the class 1 prediction tool. You see the input sequences at the top, and then there's a link where you can download the results as CSV separated file. And then there's another link which takes you to the citation. If you happen to publish these results, you can cite those references. And this is the result. First, you see the allele, and then the sequence number, then start position for your peptide within the sequence, and the end position is the peptide sequence and the method used. So I selected IEDB recommended here. So here we have got algorithm for combinatorial library, SMM, and NNLA for this particular allele. So it used consensus, and that method is mentioned here. If these algorithms were not there, it would have used SMSE2 pen, and it would have mentioned here. And this is the percentile rank at the last column. And here you can see a check box here. If you click that one, you will get an expanded result. The expanded result in the sense you will see all the results for all the 3 methods used. So for example, SMM align. So this method used SMM, align, NN align, and combinatorial library. So you have the binding affinity, the binding core, the 9 amino acid binding core, the binding affinity, and the 4 personnel rank for each of the 3 methods here. So that's the expanded complete result. And here I just want to show you how we generated this consensus personnel. So editor already showed this, but I'll just repeat that. So here for the combinatorial library, we have got personnel rank of 19.59, and for the SMM align, we have got 0.58, and NN align, we have got 2.57. So the median for these 3 values is 2.57, and that's what we select as the consensus personnel rank. And at the bottom, you have got the references for citation purposes. So this is the downloaded result in a CSV. So Excel kind of format. You can use this for further analysis, filtering and screening and all this stuff. Okay, now we saw how you can do the prediction. You have your sequence, you saw the allele, and you did the prediction, and you got the result. So now the question comes, okay, what's the threshold? So we have different, for each method we have got affinity rank, predicted affinity scores, and the percentile rank. So what to choose? So we recommend using the IEDB percentile rank. So if you use the consensus or IEDB recommended, we recommend to use the IEDB consensus percentile rank. And the cutoff guideline is what we recommend is for individual alleles, a percentile rank of 10 or less is is what we recommend and recommend as a threshold. So personnel rank it's on a linear scale 0 to 100, and low, as I mentioned earlier, the lower value being the better binder. So the peptides with a binding value, or the percentile rank less than or equal to 10 can be considered as potential binders, predicted binders. And this value actually roughly corresponds to 50,000 nanomolar. It's not exactly 1,000, but roughly corresponds to 1,000 nanomolar. So for answering our question, so we had a question in the example, identify the peptide. How many peptides does from the NSC region of hepatitis B virus binds to this allele? So we have 23 peptides that binds to this particular allele, or 23 peptides that have a predicted percentile rank less than 10. So that's our answer. So we have got 23 peptides that binds to this particular allele. And now I want to explain further on this threshold for cutoff guideline that we recommend. So for individual alleles we recommend roughly 10 as a potential threshold for selecting the binders. But this threshold is not a rigid hardline threshold. It's kind of arbitrary. We developed or we got this number from our own experiments and experience. So it's not kind of hardline number that if a peptide with 9.98 is a strong binder and 10.02 is not a binder. It's not like that. It's kind of an arbitrary rough guideline. So depending on your purposes, you can change that threshold. For example, sometimes you need to study 100 peptides from a protein sequence, and there are only 50 peptides or 60 peptides with a percentile rank less than 10. So that doesn't mean that all the remaining 40 peptides are going to be non-binders, So you can just alter the threshold and you can select peptides depending on your need. But the scale gives potential binders, so you can select the top how many number of peptides that you want to for your study. And there are cases where you want to study a fixed percentage of peptides. For example, I want to study 20% of the peptides, top 20% of peptides from my protein sequence. So you can select peptides based on that also. But this percentile rank gives you a scale of a number on which you can determine which are the top peptides to select. Yes.
And we already know so we may not see this particular thing that we are so is there we done any study about excluding the topmost high binding ones and just take the middle ones? Because the low binding is and the high binding is
Okay. The third question is, have we done any studies considering the high binding peptides with high binding activity, so that ignored or when we consider
it's deleted?
It's deleted, yeah, from the science, yeah. I don't know if we have done any. In my knowledge, I don't know anything about like that. But and when we do the epitope identification work, we don't do that. The type of work that we don't do that. So what I recommend here is if you have any specific knowledge or specific information about that kind of things, that you can consider that also. So this tool you can consider as a prediction tool. So it's not 100% perfect. It just guides you. And with your question, whether the high binding peptide, we don't know any. We haven't done any studies like that. Yeah, we can discuss about that later, but we don't know.
Question about one of the previous slides when you were determining consensus percentile rank just using the median. That's again to represent the rank.
Yes. So we have got a paper for that. So we in that study we compared the predictive efficacy of different methods with this consensus method. So in this consensus method, the scale or the measure was the median of the three methods. And we found that the consensus method is better than going with only one method.
But think, using anything that is like weighted by algorithm.
Yeah.
Right, anything like that, or
Just me. No, you are asking if we are giving weight to any particular. No, just me.
okay.
Yeah.
But you're aware that yeah, so we tried that. But maybe that's
Yeah. So, okay, we saw how we can do the prediction and we got the result. And now at this point, I just wanted to bring your attention to an issue of overlapping peptides. So I explained how the tool works. So once you submit the sequence, it basically breaks your protein sequence into all possible 15 minutes. So this is the same result that we got from the hepatitis C virus polyprotein. So if you take a close look at the top portion of this result set, you can see that all these peptides are actually overlapping redundant peptides. So this starts from 525, 526, 27, 28, 29. So it's almost redundant with peptides overlapping with 14 residues. So in a normal study, it's kind of redundant and we don't need peptides in the top. Like if you are selecting top 50 peptides, you don't need one peptide like that, 5 peptides with overlapping 14 residues in your pool of peptides. So why it happens is because since we have all possible 15 meters, these methods identify the same binding core within all these 15 meters. So if you see the binding cores from different methods, all these peptides have got the same 9 amino binding core. So what we can do to overcome this is basically what we do here is we pre-process the protein sequence. So instead of submitting your entire protein sequence for prediction, we just generate 15 meters overlapping by 10 amino acid residues and then submit these 15 meters for prediction. So why we select the 15? Because that's one of the most preferred lengths for class 2 molecules. And another thing is, when we generate 15 meters overlapping by 10 amino acids, it can capture all possible binding cores, 9 amino acid binding cores, with at least one flanking residue on both ends, so that it can accommodate the impact that's made by the binding core as well as the flanking residues. So it's not the perfect way, but it's kind of, the best possible way to capture all the possible binding cores and at the same time avoid the redundancy. And you can use any Python or Perl script or even Excel spreadsheet to generate the 15 meters from your protein sequence of interest. And another way to do this, if you don't do the pre-processing, instead you submitted your sequence and you got all the results, then you'll to remove the redundant peptides, you may have to do a post-processing. So that means you may have to remove the redundant ones. So for example, you'll have to go through the entire result and identify which are the redundant peptides and remove them. So this can be quite cumbersome compared to the pre-processing. So the approach that we recommend or we adopt is to do the pre-processing and submit the 15 minutes rather than doing the post-processing. Okay, so now we saw the prediction and we saw went through the issue of overlapping peptides and we saw how we can overcome that. Now let me explain how we can predict promiscuous binders using this class tool. So there are some peptides which binds to more than one MHC allele. So the peptides that can bind to more than one MHC molecule are called a promiscuous binders. So the significance is that we have found that these promiscuous binders, the peptides that can bind with multiple alleles, have been found to be associated with stronger antigenicity and larger, and since it can bind to more number of alleles, it can give more population coverage. And this has been found important in reducing immunogenicity of therapeutic protein, and it can be predicted using these tools based on the binding affinity. So one thing, I will explain that how we do that, and one thing to remember is that here we use a higher threshold, 20. So for individual alleles, we recommend using 10 as a potential threshold, but here we recommend using a higher threshold of 20. So it's the same way, we use the same tool, same interface, and here we select multiple alleles. So here you can use a combination of alleles, and then we get the results the same way, but here the difference is we have got the results from all the alleles intermingled. And here's the setup. So if you have a specific population in mind, or you know what all alleles you want to consider, you can use those set of alleles. But if you don't have, or you're doing a vaccine study in which you want to consider the entire global population, so this is the reference set of alleles that we recommend. So this is the most frequent alleles in the world from all the 4 loci. So this is provided in the help page. You can download this file from the help page, and if you finish, you can upload this for the prediction. So this has 27 alleles. We don't have algorithm for one, so what we normally used to use is the set of 26 class 2, most frequent class 2 alleles. So from the same example, so this is these are the peptides with the number of alleles binding. So I used this set of 26 alleles, and we found that there's one peptide that binds to 21 alleles. So for selecting the promiscuous binders, what we use is we use the threshold of 20% rank, and we select the peptides that binds to more than at least 50% of the alleles. So if there's, I used 26 alleles, so I will consider all the peptides that have got binding affinity of less than or equal to 20, or percentile rank less than or 20 is more than 13, at least 13 alleles. So here in this set, we have got one peptide with 21 alleles with a percentile rank less than or equal to 20. So that's how we can find out the promiscuous binders. So as I mentioned earlier, so these thresholds are arbitrary and on at different stages, on different periods, when we get more data available to do this training and for further analysis, we every now and then we do this analysis and we try to find, okay, is there any other method or any other approach or strategy by which we can improve the prediction efficacy, or we can improve the prediction using the same available resources, using the same tool. So very recently we did another study. So we had more data available, and we did another study, and we found that if we can use another approach, maybe we can slightly improve the prediction efficacy. So I will explain a little bit more about this strategy that we found out recently. So we had 6 data sets of measured binding affinity available. So it's not the predicted binding affinity, it's measured binding affinity. So we had data sets from House Dust Mite, Timothy, and 2 data sets from TB, and we used these 4 data sets for designing or developing this new scheme. And we had 2 data sets from cockroach and pertussis, which we used to validate this scheme. So these data sets had 15 mers, and only one, the pertussis, actually had 16 mer peptides with 10 amino acid residues overlapping, and we had the measured immune responses in terms of FSCs. And what we did is that we tried to find the percentage of peptides that's needed to capture 50% of the immune response. So using each data set, we tried to find out the half of the immune response, and we estimated how much peptides, or what percentage of peptides we needed to capture half of the person response. And we compared different approaches, for example, median with certain set of alleles, donor, the alleles expressed in the donor population, the global set of population, most frequent alleles in the global population, and arithmetic mean, median, and we tried different approaches, and we compared this with the promiscuity approach, and we found that the median consensus percentile approach is the best method. So what we did is, first we used donor alleles, that alleles expressed in the donor, and we also used the 26 most frequent alleles that I showed a couple of slides earlier. And we found that this approach, the median IEDB consensus percentile rank predicted for the set of 26 most frequent alleles, was slightly better than, not slightly, actually 5% better than the promiscuity approach. So by that, what I mean is that the top 26% of the peptides using the median consensus percentile could capture 50% immune response, whereas if you use the promiscuity approach, it requires around 31% of peptides. And we tried with different combination of locus, and we found that if we exclude the DP locus, it could slightly improve. So it needed around 24% peptide to capture 50% of the immune response. So this is not the binding affinity, but the immune response. And further on screening, we found and we selected 7 alleles, which are 3 DR1 alleles with allele frequency greater than 12% in the world population, and 4 alleles from the DR3, 4, 5 locus. And using this set of 7 alleles, we found that the top 21%, roughly 21.5% of peptides could capture 50% of the response. So this is what we recommend as of now. So, and this amount, the 21% of peptides, is roughly corresponding to the median consensus personal rank of the 7 allele 20. So if you do the, and this can be considered as a universal prediction threshold. I will explain this further here in this slide. So what you can do is do the predictions, generate the 15ers. So this is not using all possible 15ers, but just the 15ers overlapping by 10 amino acid residues. So generate 15ers overlapping by 10 amino acid residues. Do the binding prediction for the 7 selected alleles, and estimate the median consensus percentage rank. So for each allele, when you use the IEDB recommended method, you will get a consensus percentage rank, and you estimate the median consensus percentage rank, and then select all peptides with median consensus percentage rank less than or equal to 20. So that set will comprise roughly 50% of the immune response. Okay, so we are updating the tool. So every 6 months we release this later update. So we will be incorporating this feature, this kind of approach into our tool, but it will be coming in a later release. It's not available at right now. So like you input this and you will not be getting the median effort. You will have to do this estimation of median and stuff yourself. But in a later release, we will be incorporating all these features into the tool. Yeah.
So we usually come up with so many because we may not be able to do all one.
No.
To cover the whole.
Yeah. That's okay. So that's about using the class 2 binding prediction tool. So you saw how you can use the tool to predict the binding affinity for individual allele, how you can predict the promiscuous binders, and how you can use this 7 allele new approach to predict the top immunodominant epitopes. And now I just want to show you the other resources available. So, yes.
With the DQ and DP, how are you determining the way or gay?
So,
when you say like, yes, that's
so the question is,
combination.
So the question is how you determine the combination for A chain and B chain in case of DP and DQ block. So by default, what we show the A and B chain combination is the most frequently occurring combinations that we show there. And if you want to have specific A and B chain losses, you can select that separately that I showed earlier. Is that clear or?
Yeah, that's fair. I just was wondering how you determine which alpha beta.
That depends on your need, right? So if you have a donor with specific A and B chain, so if you type and you get the A and B chain, you know the A and B chain, you can use that one.
It's for the genetic frequency, you just use the pair. Okay.
Yeah, for the frequencies, yeah. We just ignore the
In
A.
other words, is it possible to pick only one of the chains and have the other chain pick at like you pick your beta chain?
Mm-hmm.
That's what we wanted. But when you pick the alpha chain based on what is most frequently occurring alpha chain combination with your specific chain. But instead put the alpha chain as a white card. Just pick only a specific beta chain and any combination of the alpha chain that science. Is it possible to do that kind of question? We have to pick an alpha chain.
So the question is whether the tool will automatically pick.
Yeah, but then we have to add multiple combinations. But we don't add multiple combinations. We can just only pick one of the chains.
That's the question.
Yeah, so the third question is whether the tool will automatically select all the possible alpha chains for one beta chain that you selected. No, the tool will not do that automatically. You will have to select the alpha chain for each beta. Yeah, that you want to select.
Good suggestion.
Yeah, yeah, we can do that. Yeah, feature. Yeah.
Okay, I might be a little bit of there are alphabets, right? No population. Is that the thing? Standard combinations, right? So the more prevalent.
Then they are in there. She wants one. That's just a better check. Let's give you all the options. Right now you have to add them.
Because there will be still a possibility of a recombination happening. Even if you know a 6 haplotype form, there are possibilities of recombination happening.
The combinations are happening there. Not as often. There are population frequencies, not full habitat.
I mean,
That's what I'm saying. Rather than
Yeah, right now you have to select it separately, but we can implement a feature in future that can select it randomly. Yeah. And coming back, here's the help or tutorial or the details for the prediction tool on the help tab. And here's the download tab where you can download all the binding data sets, the prediction scores for each of the methods. And so that's it regarding the help. And you also have the other resources like example references similar to the class 1 tool here and contact. And also, until now we were seeing the web or online version. Now we will see the standalone version. So on the same download tab, you have got this standalone tool where you can this page where you can download the standalone tool. So the features of this is that it runs on Linux. So you can download this and it runs on Linux and you can implement this on your machine, your local machine. And this is advantageous, so it's very useful when you have a large amount of data or repetitive analysis to be done. And it's free for non-profit and academia. It's available to industry also at a nominal fee. And here, this is a sample command for the running the standalone version. So here you were asking whether we have a package for standalone package for IEDB recommended. So we don't have separate packages for each method. It's the same one for class 2 and another one for class 1. So here you can choose what method you want. So you choose the prediction script and choose the method and then select the allele. And in case of class 1, you will have to select the length. But here you don't have to select the length, it's fixed at 50 and the input file, and you can get the results into an output file. So this is a sample command for using the standalone version, and more detailed instructions are available in the README file, which will be downloaded along with the tool. So, and the next version is the API or the RESTful interface. So more details on this is available at the Tools API tab at the main analysis resource web page. So this tab is not on the class 2 tool, but it's on the main analysis resource page. So it describes what this is. It gives sample commands here, and it's also explaining what are the different parameters which can be used here. So both class 1 and class 2 tools are available. Also, some of the processing tools are available as API. And what this does is that it actually collects your parameters, input parameters, and sends the request to server, which is here. So it's not running on your local machine, and it's not using the web interface. So that's the difference between the other two versions. So it's collecting your input parameters, and it's sending the post request to the server, which is located here, and it does the prediction and sends the results back to you. So the advantages for this version compared to the others are that you don't have to install the standalone version locally on your machine. You don't have to depend on the web interface, but still you will need the internet. It's not locally run, so you need the internet connection, but you don't have to go to the web interface and copy paste and like that. And the requests are sent to the IEDB tool server here at LGA, and it's freely available to all users. And you don't have to worry about updating or new releases. It's automatically updated. For standalone version, when you release a new version, you will have to update that, but you don't have to worry about that when you use this API. And here's the sample command for class 1. So you select the method. So here is the recommended and sequence. You can provide the sequence here and allele. So you can use multiple alleles here, which each separated by comma, and you can also choose the length for each allele. And in case of class 2, and this is the server address. And for class 2, the same method, sequence text and alleles. You can use multiple alleles here, and you don't have to specify the length. And here's the same server URL. This is the sample command that I ran for the API. So this is for the class 1. So you can just get results like this, or you can take it to an output file. So that's it. And in this session, first we had a comparison of class 1 and class 2 tools, and we saw what are the major differences, and we saw how the tools work, and we saw different versions of the tool, the web for online and standalone version, and also the API. And we saw how to use the tool for doing the binding prediction for individual alleles, how to predict the promiscuous binders, and how we can use the new approach using 7 alleles to predict the top immunodominant epitopes. And we also went through the different threshold recommendations for using different methods and alleles, and we also saw other resources. So, and before I go to the exercise, I just want to mention that these are prediction tools. So when I go to different conferences and do the presentations, many people have concept that okay, this gives the real epitope. You give the sequence and it gives you the real epitope. So why do you find this peptide gives a very high affinity, and why does it bind? I did the exercise. So it's not correct to have that kind of concept. So this is just a guidance. It just predicts, and the final validation is you need to do the real binding. So why do we use this prediction tool? Because you can save a lot of money and save a lot of time. So from a set of 1,000 peptides, you can reduce that peptide pool to like maybe 100 or 50, and you can save a lot of time. So it's not the final cutout answer. Okay, you get all the final epitope. It's not like that. So you have to keep that in mind. And by this, of course, you can save sort of time and energy, but it's not the final definite answer for all the epitopes in some particular sequence or pathogenic organism. Here we have got a small exercise. So I hope you have the sequence and alleles in your email. So it's very short and simple exercise. Predict the alleles from the given set of 6 MHC class 2 alleles for this particular peptide that can bind. So we have got 6 alleles, 2 from DP locus and 2 from DQ and 2 from DR1 locus, and we have a schemer here. So find which all alleles can bind to this peptide. If you have any question, just raise your hand. I can help. Yeah, we have got roughly 5 to 10 minutes. It's very easy. 5 to 10 minutes you can try, and if you cannot, and I will take you through the exercise after 5-10 minutes. Okay. So I hope most of you got the results. So here's the question, and what you should have done is you did the binding prediction and select the peptide that has got the consensus percentile rank less than or equal to 10. So you can paste you must have done this. You pasted your sequence here and selected the method as IEDB recommended and selected all the alleles that was in the question. And then you should have got this result. And you have 2 peptides, 2 alleles that are binding up with, the percentile rank less than 10. So these are the 2 alleles that are predicted to bind to this subset. That's our result. Okay, if you have any specific question, you can ask me now, or we have digital more sessions, breakout sessions in the afternoon. We can have more discussion at that point. And please remember to give feedback for any suggestion or any other feature that you want to see in the tool, or any other tools that you would like to see in the IEDB package that you normally use. It can be some other tool that you use internally, or if you have seen somewhere else. So please recommend that, and we'll be happy to implement that in our IEDB tools package. Thank you.